Good morning, everyone. My name is Johan Debayle. I'm professor at Saint-Etienne, a graduate school of engineering and sciences located in Saint-Etienne, close to Lyon in France. First of all, I would like to thank the organizers for inviting me to this conference and to give me the opportunity to show you some research work we carry out in my group at Saint-Etienne. So thank you very much. For this talk, I would like to show you how one can extract some useful information from images coming from process and chemical engineering. So I'm going to speak about image processing, image analysis, pattern recognition, as well as image modeling with the use of stochastic geometrical tools. So we are going to play with 2D images representing a population of particles, and we would like to extract geometrical and morphological characteristics, such as the particle size distribution, for example. As you know, granular media are used in several industrial processes in chemical engineering for different application areas, such as energy, nuclear, pharmaceuticals, aeronautics, food industry, and so on. For sure, one objective of the companies is to better control and optimize these processes. And for that, it's necessary to have a better understanding of the physico-chemical behavior of the granular media. For example, when you have an interaction with a gas or liquid in a flow, or when you have a thermochemical transformation. And one key point in these physico-chemical models is the geometry and morphology of the granular media. And for that, we can use image acquisition and image analysis to access to this information. The context is the following one. We have some 2D images representing a population of particles. And when I speak about particles, it's in a very large sense. It could be crystals, bubbles, droplets, and so on. You have here some examples of 2D images we are working on. We have some oxalate ammonium crystals in the first 2D optical image. In the second one, with our partners from CA, we have some gas bubbles in the liquid flow. On the third one, you have some sand grains. It's just a 2D slice of X-ray tomography. And the last one is about zinc sulfide aggregates, which are used in paint pigments. So when we have these 2D images, the main objective is to characterize, to quantify the particles. So we speak about size, for example, with some characteristics such as area, perimeter, diameter, and so on. We speak about shape independently from the size. So we're interested in the elongation, roundness, fractality of the particles, and also with the spatial distribution, just to know if the particles are homogeneously dispersed or if they are in clusters, which can be very useful when you try to analyze some aggregates, for example. And as you can see, classical image processing is not enough because you have a lot of superimposition, because you have just some 2D images. So you have a 2D sensor, you are looking at 3D particles, and you only see the shadows of the particles inside your reactor, for example, in chemical engineering. So the main difficulty is to separate, to individualize these particles in order to be able to measure the different particles in terms of size, shape, and spatial distribution. In order to extract the geometrical information from these 2D images, we propose two main ways. The first one is about advanced image processing and analysis, or pattern recognition, where firstly we try to separate or to individualize the particles using a specific analysis. And after that, for sure, it's very easy to fully describe the particles in terms of size, shape, and dispersion. So for example, on the first image, we have identified some crystals with a polygonal shape, and on the second one, the gas bubbles with elliptical shapes. And for sure, it's easy to extract the particle size distribution once you have individualized the particles. The second method we proposed is very different in the sense that we do not make image processing, image analysis to recognize some particles, but we use a kind of inverse approach. For example, if you start with this 2D gray level image, you can, with image processing, you can simplify the image with image segmentation. You can binarize the information. So black is the crystals and the white is the background. And the objective here is, in fact, to model and to simulate some images which are representative of the real data. So it means that on the right part, you have what we call a digital twin, because it's, yes, a simulation from a geometrical models with different parameters, and you try to change the value of the different parameters in order to fit this simulation to the real data. And if you do that, you can say that you have the same geometrical and morphometrical information from this 2D images, the real one and the simulated one. And for sure, if you make this fitting, in fact, you can say that, as I told you, the size distribution, for example, is the same. And for sure, in the geometrical model, you have a lot of parameters which are related to the size, shape, and so on. So, in fact, it's a very different approach, as you can understand, because you do not make some pattern recognition techniques directly, but you simulate and you try to fit your simulation to the real data. Okay, now I'm going to speak about these two kinds of methods to give you more details, and with a specific application to crystallization processes. So in fact, applicative context is the following one. So it's for a pharmaceutical issue where to produce some active ingredients for drugs, you have a specific step, which is the crystallization. It's a transition from a liquid phase to a solid phase, where you have some events like nucleation and growth of the crystals. And the quality of the drugs depends on the geometry of the crystals. So for the industrial companies, it's necessary to control the geometry of the crystals all along the time. For that, you have different techniques. You can use some offline granulometry techniques where you have to make a sample, and with some shape assumption, it's possible to extract an equivalent diameter, for example, of your different crystals. But which is more useful is to use online granulometry techniques where you have a sensor inside your reactor, for example, and you make some image acquisition, and with some image analysis, it's possible to extract geometrical and morphometrical information about your crystals. On this slide, you have an illustration of the experimental setup we have in our lab. So on the main part, you have the reactor with the crystals and the liquid inside, and a stirrer to mix the flow. You have different kind of sensors, and one of them is the in situ image acquisition probe with a CCD camera, and so it's possible to capture images of the crystals. Here are some illustration of 2D images of crystals we can acquire with this kind of sensor. You have here 4 images where representing different kinds of crystals, and you can imagine that it's not very easy to extract geometrical information of the crystal with classical image processing. As I told you, from these 2D images, the scientific challenge is to extract the real-time granulometry. So we speak about size and shape distribution of the crystals all along the crystallization process. So it means that we would like to extract this granulometry at any time. And for sure, we have a lot of difficulties when you are looking at 2D images. Firstly, the problem of out of focus. So you have some particles which are not in the focal plane. So probably it needs some inverse filtering techniques to extract the real size of the particles. Second point, we have some overlapping problems. So it means that classical image segmentation techniques do not work. Thirdly, we have some 2D projection of our 3D particles. So even if we extract the 2D size and shape of these particles, we have only the 2D information. And for anisotropic particles, elongated particles, one can expect a thinner characterizations, for example, with the 3D size, the 3D shape. And lastly, it could be very difficult when you are at the end of the crystallization process because you have a high density, and so it's much more complicated to individualize and to extract the particle size and shape. Actually, we tried to solve all the problems I told you before one by one. So the first one is about out of focus. And from this 2D gray level image, for example, we firstly try to segment the image with the watershed transformation. So here you can see that you have one region for each particle. But at this step, we do not take care about the superimposition or the aggregation of the crystals. So for example, on the right part, you have surely an aggregation of different crystals, but we consider that it's only one in one region. Once we have identified these different regions, we can make some specific image measurement about the variance, for example, of the gray levels, to know if the particles are on focus or out of focus. So on the image below on the left, you can see that the black region here are considered to have some out of focus particles, and the white part you have particle on focus. And in fact, the final step is to make a specific process in relation to this characteristic out of focus or unfocus. So it means that when you have some unfocused particle, it's easy to extract the contours. So you can see on with the green contours here, if you can see, we have easily extract the contours of the different particles, and in this way we are able to measure the size and shape of these particles. But for the blurred particle, because they are out of focus, we firstly extract the contour, but we know that it's not the good one, and we make an inverse filtering, such as deconvolution filtering, to extract the real contour. And one of the parameters in this deconvolution filter is related to the degree of blur. So it works well on this kind of images. And yes, as I told you, we have a specific process to identify the focused or the blurred particles. So after that, once we have extracted the contours of the different particles, it's very easy to compute the particle size distribution, for example, with the equivalent diameter. And you can see here two particle size distribution at two different times, 2 minutes and 5 minutes. And you can see that you have for sure an evolution of this particle size distribution, because here we have a growing of the particles, and you can see that at 5 minutes you have much more larger particles. So it works well, but the main problem is the particle overlapping, because as I told you, we do not take care about the superimposition or the aggregation of the particles, because we consider at this step that it's only one particle. So we have to now to take care about that. So how can we identify particles which are overlapped? And so we propose a specific method here for this kind of crystals. So we start from the 2D gray level image. Firstly, we try to identify some specific point, which are the corner points here. You can see on the upper right image. In the lower left part, we extract also the contours of the different particles. But this part is not very easy, in fact, because you can see that with the crystals, we have central transparent part where the colors is, yes, closely to. After that, it's easy to extract the size distribution. So here it's interesting because we have some particles where we are able to measure the length and the width. So we have much more information in comparison with just an equivalent diameter. And for sure, this one gives information about the anisotropy, the elongation of the particles. So you can see here an illustration of the particle size distribution in 3D with the two first axes related to the length and the width of the rectangles. So it works well on these superimposed particles because we have an a priori about the shapes we are looking for. But nevertheless, we have a main limitation is that we extract only 2D particle measurements. It means that if you are looking at the particle with a different view angle, for sure you don't have the same measurement. So we have a bias for that, and we would like to extract 3D information about these 2D images. It's the next step. So on this one, we are, as I told you, interested in the 2D projection problem. And so, for example, on this image, you have 4 consecutive images in the video, in the image sequence, and you can see what is highlighted in red here. It seems that you have the same particles, but with different view angles, because as I told you, the particles are moving in the reactor, and so we can expect that the particle is moving, and you can see different views to the view angles of your particles. And so if we are able to track this particle, we can expect to reconstruct the 3D shape. And so we have worked on these topics. And so finally, the challenge is, the question is the following one. Imagine you have, for example, the 5 2D silhouette of your 2D shadows of your particles, because you make this tracking. The question is, what is the real 3D object? Is it a square, for example, a cube here, or more a parallelepiped shape? And so by measuring some geometrical and morphometrical information, and by using some maximum likelihood estimation, it's possible to identify the most probable shape. And so we can combine this approach with the previous one. So for example, on the image on the right, imagine you are able to identify the particles, and also you are able to track each of the particle. You can make an assumption of the crystal. For example, you have a 3D rectangular cuboid, and by looking at the different 2D views of the same particle in a sequence, you will be able to extract the 3D information. And so it's very interesting because you have a kind of 3D reconstruction of your particles. So here you can see the particle size distribution, where the size is related to the volume, so it's a 3D information. And you can see that you have an evolution all along the time for this characteristic. But the main problem here is that when you have a high density of inside your images, it's too difficult to identify and to track the particles. So we are going to use the digital twin I told you before. So it's a very different approach where we do not make real image processing and analysis, but much more image modeling, and we will try to fit a geometrical model to the real data. So now we are going to speak about geometrical modeling, as I told you. So the first step is to try to simplify your 2D gray level image just by image binarization. So here you have an example. It's not so easy because, as I told you, you have a transparent part where the colors is very close to the background, so it's not so easy. But we can do that. And so if you have this image, now we would like to know how we can define a geometrical model of such images. It means how we can simulate some images which are representative of this real data. And for that, in this case, with these crystals, we can consider that we have a population of 2D random rectangles. So it's an assumption that the shape is close to rectangles. So how we can define a geometrical model in order to simulate some virtual images of this population of rectangles. So we speak about a geometrical digital twin. So for this model, we have different parameters representing the particles. Firstly, the number of particles, which is denoted here by the parameter n. We have also for each particle its position with the coordinates x and y in red, and also the shape with the width, length, and orientation theta. And we consider that all these parameters, these values, are random. Why? Because we would like to be able to define different samples of the same population. It means, for example, if you have imagine you have your sensor in your reactor, you only see a small part inside the reactor, and if you move your sensor in another part, you can consider that you have the same population of particles, but for sure you can see different crystals. Also, if you have your sensor which is fixed in your reactor, at a specific time you can see different crystals, but if you look at just 2 or 3 milliseconds after, we can consider that you have the same population, but for sure not exactly the same crystals. So it's the reason why we would like to have some random values to be able to simulate different samples of the same population. So in order to represent these random values, for sure behind you have some probability distribution. We consider that we have some dices representing this probability distribution. So you have a green dice for the number of particles, you have 2 red dice for the position, and 3 black dices for the shape. So what I propose you now is to play with dices to simulate one image. And so in the literature you can find different models, and one of the most simple one is the Boolean model. So I have to get a value of a number of rectangles to simulate my population. So I can throw the green dice and imagine I get the value n equals 8. Okay, so I start with the first one. I put I throw the red dices to have just one position, x and y, you can see here, and also the black dices to have a specific a, b, and theta. So I have a first rectangle related to these random values. And I continue because, as I told you before, my green dice give the value n equals 8. So I have to continue until this value is reached. So I continue with the second rectangle. So I throw again my red and my black dices. I have a second rectangle, and I continue until n equals 8. Okay. And I can make the intersection with the observation window. And here is a simulation of my Boolean model of rectangles. And so this simulation I showed you before, it was just one realization of my geometrical model. And for sure, if I play again with my dices, for sure I will have different simulation. So you can see here 3 different realizations of my geometrical model with exactly the same dices, but just I throw my dices, as I told you, you have some random values. So it means that I have the same probability distribution, and it's just free realization of this population. And we can say that they are statistically equivalent because they come from the same distribution. But for sure, we would like to have a flexibility of the model in order to be able to simulate different kinds of population. And we can do that very easily by changing, in fact, the probability distribution, or from an analogous point of view, by changing the number of faces and the values on each dice. So for example, if I play with a specific set of dice, I can have this kind of realization. But if I change my dices with different faces, different values, I can have, for example, this kind of realization where you have much more rectangles, which are smaller on average. Or I can simulate also some rectangles which are close to squares. So just by changing my dices, so as I told you, by changing the probability distribution. So for this application, we have defined a geometrical model representing a population of rectangles. So we are able to simulate different images of a population of rectangles. And now the idea is to try to fit the model for sure to the real data. So on the left part, you have the real image. On the right part, you have a simulation. And so we would like to try to get the optimal parameters in order to say that these two images are very similar. And for measuring the similarity, we will use some global image statistics. So for sure, it's not similarity pixel by pixel, but it's just with some global statistic on the global image. And for doing that, in fact, it's an optimization problem, because if we would like to fit the model to the real data, we have to find the optimal parameters, and so to find what are the probability distribution behind, or in other words, what is the set of dice I have used. And so for some specific model, you have some analytical expression where you are able to directly find the optimal parameters, but generally we need numerical optimization to find this model parameters. And so at the end, for sure, it's the final point, in the sense that if it was possible to fit the model to the real data, we can consider that the granulometry of the real data and the granulometry of the model is the same, because you have similarity between these two kinds of images. And so if you have the same granulometry, in fact, if you look at the model, in fact, with the optimal parameters, for sure, some optimal parameters, for example, if you look at the black dices, they are related to the shape of the particle. It means that if you fit your model, you know the granulometry of the model, because you produce a model, you simulate the model with some parameters that you know, and you can consider that the black dices are also related to the shape of your crystals in the real data. So it's the reason why I speak about inverse approach, because here you simulate an image with some parameters that try to find the optimal ones to fit the model to the real data. And without any image processing or analysis, you are able to identify some geometrical characteristic of your crystals. To go further also with this geometrical model, we are able to extract some 3D information, in fact, because we can imagine a 3D models. So here it's much more complicated, because for sure you have more parameters in your model. Also, you have to take care about the particles that should be hard particles. So it means that you don't want to have intersection between the particles as in the real life. And after that, on this model, you can simulate a 2D projection. So you have a 2D simulation that you try to fit again to the real data. But at the end, if you consider that you have the similarity on the 2D images, you can expect that you have in reality something which is close to your 3D model. And with your 3D model, you know the 3D parameters, so you know the 3D size and shape distribution of your particles. Okay, and you can see here that we have used this kind of models, maybe not this one I try to explain you because it was the most simple model, but we can imagine different models with different parameters. And here, for example, to the application about liquid gas flow, you have here the real data, and you can see here the geometrical model which has been fitted to the real data. So you can see here that you have a high density, and so if you try to individualize all the gas bubbles, it's too difficult. But with this kind of inverse approach, you are able to simulate something which is similar to the real data, and you consider that the granulometry are the same between the real and the geometrical model. And so it means that indirectly you get the size and shape distribution of your gas bubbles. Also, for fuel cell electrode microstructure, we have worked with other specific geometrical models coming from stochastic geometry, where here you have a 3D image coming from tomography, where you have two solid faces and one porous face. And we are able to simulate something which is very similar by playing with a specific model. So again, we have defined a model that we can fit to the real data, and as I told you, inversely to be able to extract some useful geometrical and morphological information about the different phases and also the interphases. So now I can try to conclude on this work. So I tried to firstly show you some techniques about image processing and analysis to try to individualize the particles, for example, with the crystals for the pharmaceutical industry. And once you have identified, individualized the crystals, for sure it's easy to fully describe the particles in terms of size distribution, shape distribution, or spatial distribution. The second part was about image geometric modeling, and I think that here it's much more powerful because you can process images with a low or high density, and also you can retrieve some 3D information with some specific model. So I recall the main step. You have your grade level image, you simplify your image in a binary one, and you try to simulate something which is close to the real data with a geometrical model. And if you fit the model to the real data, you can consider that you have the same shape and size distribution of your particles. And for sure, in your model, you control the parameters of your model, and some of them are related to the shape of your particles. So it's the reason why by this inverse approach, simulation and fitting, it leads to the morphological characterization of your particles. All the numerical simulation have been done by homemade softwares in our group. And we are able also to validate the models with some real experiments with calibrated particles. So it means that, okay, we have a specific population of particles, for example, some spheres with a Gaussian distribution, and we can try to generate our model and to retrieve the good distribution and to compare if it's good or not. And also we can validate with some numerical experiments. So it means that we can imagine that we have a model with some specific fixed parameters. We make one simulation and we consider that this simulation is a real data. And after that, we can try again to simulate and to fit a model to the real data to find the first parameters. At the end, I would like just to highlight that from a theoretical point of view, we can have some analytical expression for very simple models, such as the Boolean model. And it means that in this way, it's not necessary to use numerical optimization, but you have some analytical expression that give you directly the parameters of your model that fit to the real data. As scientific challenges, in fact, we can consider models much more complicated, for example, with interacting particles. So it means that you have some interaction with attraction or repulsion between your particles. So it's possible to play with this kind of models, but for sure you have much more parameters, so it's more complicated for the optimization process. We can also imagine some dynamic models where you have over parameters related to the time. Okay, so you have over dices, over probability distribution. And currently we are also worked on this geometrical models with the use of machine learning tools. Why? Because as you know, when you play with machine learning, one key point is to have a very large database with a lot of flexibility to be able to have an accurate training. And with this kind of geometrical modeling, you are able to simulate a very high number of simulations. So it's some virtual images. So you can very easily simulate a lot of images, and you can try to train this information by your machine. So I think it was my last slide. So again, thank you for your attention, and thank you to the organizers.